All right. Well, basically, you have absolutely no idea why you're here right now. Neither do I. I'm deciding to start making little recordings of my self-study progress because I think it would be fun to, well, A, be able to learn the material well by teaching others, and B, I think it would be cool to keep a record of what I've gone over in the past so that in the future, when I'm uh, the most dangerous man on the internet, I will be able to look back at my roots and anybody who's trying to defend against an ethical attack that I may uh, let's just not go there. Anyway, anyway, I'm just going to use this as a creative outlet to explore topics in computer science that I'm interested in, which happen to be right now at least cybersecurity and artificial intelligence. I think they're important and they are interesting. So that's what we're going to do here. I'm just going to explore some topics and learn about them and also teach them kind of to help me learn. So if you enjoy them, that's great. If you don't enjoy them, that's great too. I'm just going to do this mostly as a record for myself, but if I end up inspiring somebody or inspire somebody pretty much, yeah, I don't know. If someone likes it, that's cool. I'm honestly just happy to make anyone else happy. So if even one person thinks this is interesting, then that's great. That's awesome. Anyways, kind of off topic, but let's get into the meat of the first day. Anyway, so what does it mean to be technologically unstoppable? Well, who knows? But my plan is to become the most dangerous man on the internet, and to do that, I'm assuming that I would have to become technologically unstoppable. Um, and so that makes me question. So with the topics that I'm interested in, cybersecurity and machine learning, basically, what are the possibilities? What can I do combining various topics and skill sets that I will acquire? Basically, what can't I do? What is not possible? What is possible? There's a lot of things that are known to be possible and a lot of things that are known to be impossible. But a lot of things that were impossible in the past or thought to be impossible are clearly possible now. I'm sure like back in like the 12th century, they never thought it'd be possible to go to the moon, but we've done that multiple times with and without humans, and we literally have a helicopter on the moon that's been flying. So that's not to say that everything is impossible. Everything that we think is impossible is actually impossible. So who knows? Maybe we'll make some discoveries here that are going to be life changing for the better, hopefully. Yeah, for the better. And then the most important question is, will I make it on a watch list? You will have to, well, let's hope not. I'm assuming not, but it's never really good to assume. I'm hoping not, because I'd like to be able to still travel, and that is not possible if you're on a watch list. But I'm not planning to hack unethically, okay? If I ever become somewhat of a hacker, I will promise to only hack ethically, unless it's my own hardware. Then I will hack myself unethically. I think that is I think that is ethical. It's ethical to do unethical things to yourself, kind of. Um, there are restrictions on that, so do not take that at face value. I am not a life advisor, financial advisor, whatever I need to say to not be liable for anything. Basically, I believe that it's okay to do unethical hacking techniques on my own software and devices because it'll only be affecting me if I can prove for certain that that is the case. So we're getting too far into this because I don't even know how to hack. So, but that's a little bit further down the line. Anyways, let's get into um, kind of the first lesson. So basically, what I've started learning in the past few days. So we're gonna go over some basic fundamental ideas behind how machine learning and artificial intelligence are integrated on a more theoretical level. So buzzwords, yay, right? Artificial intelligence, machine learning. I'm sure you've seen them all over the news. ChatGPT, all the likes. That's not really what makes me interested in these topics because to be honest, I could care less about ChatGPT. It sucks at chess and it's apparently not that great at taking tests. Not that I would ever use it to take a test, but I mean, it's a cool idea, right? It's a cool idea. But it's not what I personally find interesting about artificial intelligence. I think there are plenty of other very exciting applications soon to be discovered, hopefully by me and this series of becoming the most dangerous man on the internet. Anyways, so right. So what is machine learning? I mean, to most people, I think it's easiest just to think about it as a black box. That's basically how I have thought about it for the longest time. It's just like, stuff goes into this black box and we get stuff out, whether it's like text in the format of a response, like through like GPT systems. It can also take away jobs. It can also produce bad chess bots. These are all just like jabs at chat GPT, but it's whatever. There's a lot of good to come out of artificial intelligence. There are many practical applications, for example, for healthcare and for predicting weather catastrophes and very very wholesome and societally enriching possibilities. There's also the latter where it's like using artificial intelligence for the greater bad, not the greater good. um as I kind of stated here, it seems like there's infinite possibilities for good with artificial intelligence, so I'm hoping to explore some of those, and maybe even explore ways to combat the infinitely bad possibilities that AI produces. But what does it really mean for a system to be artificially intelligent, or how do we kind of teach these systems? Well, I'm not exactly sure. I've only been studying this for like a week, so I'm no expert. And basically you'll find out in the next slide. But I was getting into the basics of how neural networks are kind of implemented, and those are the basic framework upon which systems are built to learn and adapt to data inputted. So with that, let's jump into the first slide. Also, in the description, I will post the resource that I've been using to learn about neural networks. It's a very in-depth book that's very beginner friendly, and it is free online and it is wonderful. So if you're interested, definitely check it out. If you're not, that's completely fine. Do whatever. Do whatever. Anyway, so let's get into this. So how do I want to start this? Basically, a neural network is going to be a network of these theoretical nodes that you send data to, and through a series of decisions and data transfers, you end up getting an output that hopefully resembles the expected output. Like the very basic example of a neural network is one that, well, like the book suggesting, it will identify the character that's been written. So if you like draw a digit, it'll use some math to figure out kind of what that digit should be based on the pixel values, and a bunch of crazy algorithm stuff, which we'll explore in the near future, hopefully within the next few weeks or something, which is cool. But let's just think of it now as basically data going in, a decision being made, and then data going into a node. A node as in like, think of it as like a question, right? You take in information, and then in your little question ball, you kind of evaluate that information, and then you give a decision or an output. And so one of the most simple implementations of these decision balls, as I would call them, I don't know if that's the best way to say it, but whatever, are known as perceptrons. And there's a pretty in-depth history about this, which I'm not going to teach because I don't really care for the history too much. It's cool and all, but yeah, it's a starting point in neural network implementation is the best way I could say. I'd say it's similar to flipping a coin to make every decision, right? Because a perceptron, the whole basis of a perceptron in a way, is that it has a binary input and a binary output. So it takes in data either as a yes or no, or like a 0 or 1 kind of, and then only outputs a 0 or 1. So there's only 2 possible inputs and 2 possible outputs. So it's pretty simple. It turns out that you can actually solve, well, I shouldn't say any problem, but it turns out that, well, we'll find out. Anyways. So basically how can I describe this in like a simple example, I guess, would be like, if I were to ask the question, can I code? And let's say there's 2 factors that kind of really affect whether or not I can code. Let's just label factor C to be, does the question, or can I code? Factor 1, does me being able to code require that I have coding knowledge? And we'll just for an example, label that as variable C. And then Another factor could be, is there good music playing? And let's label that factor. And this is kind of a really stupid analogy, but basically, let's say we have our decision ball here, and then our two inputs, which are either requires coding knowledge, doesn't require coding knowledge, good music is playing, good music is not playing. And then we have to kind of figure out, okay, can I code or not? Well, it turns out that it actually depends on more than just the inputs, because we can actually put in, these things called weights. So let's just say weight 1, weight 2, and those weights will essentially determine the importance of a certain input. So let's say that weight 1 is infinitely large. Now, if it's infinitely large, well, yeah, that makes sense. Well, okay. And then let's say weight 2 is like 1, because like really it doesn't really matter if good music is playing whether or not I can code. But basically, let's say the question is asked, can I code? And input C, does the problem require that I have coding knowledge? If it does, then, whether or not good music is playing has less of an impact on whether or not I can code. This is a really stupid analogy. Basically, I'm just going to boil it down real quick because I did the worst explanation right there. But basically, each piece of evidence that comes into your decision has this, there's an idea of a weight, and that kind of impacts the importance of a decision, or impacts the importance of a piece of evidence. So some pieces of evidence might have a much greater effect on the output than others. So for my coding example, it's much more important that, so it's my ability to code a question is more related to whether the question requires a lot of coding knowledge or not a lot of coding knowledge than it does on whether or not good music is playing, as much as I don't believe that, because I think I code better when there's good music playing. But anyway, that's basically a simple example that was really drawn out and could have been much better portrayed. But yeah, so basically the next obvious question would be, how does this decision ball work? How is it that we can take in these pieces of evidence and then evaluate and determine what our output should be? And it turns out that we are going to need math. Of course, we need math, because this is how life is past the age of 12. Well, never mind. So yeah, it turns out we need math. It's not incredibly difficult math. It's just you have some matrix multiplication and addition, but it's kind of just abstracted away to this idea of taking so there's a long-winded way of saying that we need math to basically determine whether or not all of our inputs and their relative weights can be, let's say we're going to evaluate that to something known as a cost. So how much does it cost, whatever. And then we want to test whether our data basically surpasses something called a threshold. And so this is similar to, if you're familiar with how neurons work, there's like there's an activation threshold in the the voltage, or I don't know the electronics of it, but not electronics, whatever. There's like a current threshold for where a neuron will actually activate and do its thing. And that's similar to kind of how this works. So you have all of your inputs coming in that each have their own weights, and we get this. So basically what this is just this right here can just be seen as like the sum of all the weights times their relative inputs. So it's basically just a weighted sum of all the inputs. Now B, we'll talk a little bit more about this in a little bit, but B is basically what's known as the bias, and bias is represented as bias represents the inverse of the threshold. So if the threshold is like 10,000, then the bias is negative 10,000, and vice versa with swapping signs. But basically, so for a perceptron, we will basically get, I'm not that good at explaining. It's going to take me a little bit. Okay, so let's just quickly condense this down and say that Z is equal to the weighted sum plus the bias. So basically, what is our question ball evaluate to after it's taken in all the evidence, weighted sum, blah, 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 all this math, this abstract stuff that we don't need to worry about. So if that value is less than or equal to what we'll call the threshold. I can't spell, but it's fine. Then if it's less than the threshold, then we won't get an activation, and we'll say that the output is 0 because it has failed. Otherwise, if the cost of the question ball, if the question ball evaluates to whoops, that's not greater than 0, that should be greater than threshold. So if we surpass the threshold, then boom, we've succeeded, and we'll output a 1. And that output may go to another node, which goes to another node, and there's just this network of nodes. And this is good implementation and all, right? It's pretty simple. There's 2 inputs that you can have, 2 outputs that you can have. It's a nice start to implementing the idea of a trainable network, a network that, well, we'll get more into training later, so I don't want to talk about too much. But basically, how good is this method at what it's supposed to do? Well, it turns out that it's not that great for one obvious reason, which we'll get into in a little bit, but it's actually, like, the theory behind a perceptron is good because you can technically solve any problem with a network of these. Now, you can't train a network of perceptrons to do physically any problem. I don't think that's possible for any artificial intelligence. I think there are things that are completely unsolvable with AI, but I don't know. We'll discover that in a bit, in later weeks, months, years. I don't know. So basically, we want to know, okay, well, this is good and all, but, like, how good is the perceptron implementation? Or what can it do? And it turns out, if you're familiar with like circuits and discrete math, there's these things called NAND gates, which is basically a gate that takes in 2 inputs, and will produce either a 0 or 1 depending on the 2 inputs. So a NAND gate will produce a 1 if the 2 inputs are both 0 or they're different, and it'll produce a 0 when they're both the same because it's an AND gate. So it's just formal logic stuff. It's not the most important. What is important is that it's been proven that any problem can be solved using a series of NAND gates. And so it follows that if we can somehow emulate a NAND gate with perceptrons, then we should theoretically be able to solve any. I'm not sure about the extent of any in here, but we should be able to solve just as many problems with perceptrons as we can with NAND gates. And it turns out that we can actually implement a NAND gate with perceptrons. I'm not, this is not the most interesting point to bring up, but I think it's still important to finish it. So yeah, so as we were talking about before with weights and biases, it turns out that if we have a single perceptron that takes in 2 inputs, each input having the same weight of -2 and a total bias of 3, it turns out that this actually emulates a NAND gate through the math, because if this inputs, let's say if one inputs a 1 and one inputs a 0, then the weighted sum of -2 and 0 times -2 is going to be -2, and then plus 3 is a 1, which is it'll plus the bias will be a 1, so it'll output a 1, which is because it's going to take me like a few weeks to get good at explaining stuff, so give me a chance. But basically, this emulates a NAND gate. It's not the most important, so I think for now it's almost more important if I just move on a bit. So that, just abstract away and believe me that this NAND gate here allows for universal computation. And so in our table here, we see that perceptron is capable of universal computation. We'll explore that in a little bit, but the most important point is, are perceptrons trainable? And there's a lot of math involved in how the training aspect of a neural network works, and we'll get into that in the next few days, weeks as well, with concepts like backpropagation and stuff, which that's like a buzzword. I don't really know what it means yet, but I've heard that it's important. So backpropagation, we'll get into that soon. And it turns out that perceptrons are actually not trainable because of their binary input-output concept. In order for something to be trainable, you want to be able to tweak the weights and biases of each input and each input to make small changes in other inputs and outputs to eventually make a series of millions or trillions of small little changes that eventually get your system to output what you want it to based on the input data that you've trained it on. And it turns out that perceptrons are not trainable because, like I mentioned, they have a binary input output. And so you can make really small changes to the weights and biases still, because weights and biases can be whatever you want essentially. But because the input and outputs are binary, a really small change could change one of the inputs from a 0 to a 1 or a 1 to 0, which is not a very small change. That's a pretty big change for a one node to completely switch what it's doing. It's just not good because you cannot make the small changes that are necessary for a sound trainable network. And so that brings us to the question of, okay, well, can we do better? Clearly we can do better because we have systems like ChatGPT. So who am I to sit here and tell you that we can't do better? We can definitely do better. It turns out another implementation of this kind of system, they're known as sigmoid neurons. And I put this awesome picture of a puppy here because they are trainable, questionable, question mark. Puppies are trainable, some of them. And it turns out that they're very similar to perceptrons. In fact, you can basically approximate perceptrons with sigmoid neurons, but that's not really important right now. What's important is the fact that they are trainable, because the most important point about a sigmoid neuron is instead of having a binary input, they have an infinite number of possible outputs and inputs between 0 and 1, rather than being only 0 or only 1. And this is important for training because you can make small changes to the weights and biases, which then could change one of the inputs and outputs to be slightly different, anywhere in between 0 and 1, rather than being 0 or 1. And there's some other fancy math involved here with things known as activation functions. And there are quite a few activation functions. One of like the more basic ones that's definitely slower for, or I've heard it's slower for training systems, is this here, the sigmoid function. It's pretty weird. There's another one, I think it's called like it's like I'm not exactly sure what it is, but basically it's the max of 0 and the cost, and it looks like this. It's another function that's basically a lot more efficient for training. We'll probably learn more about that later. It's not the most important for basically describing what a sigmoid neuron is, but so yeah, we know that we can. Well, we don't know because I haven't explained it to you. But it turns out if we are using a sigmoid-based network system, sigmoid neuron-based network system, we can emulate perceptrons by creating thresholds that approach positive or negative infinity. And there's some math involved in proving this, but it's not the craziest. So it turns out that if we use these thresholds that are on either end of infinity, there's not really an end, but you can essentially get a binary input output. And so we can, from that say, okay, well, if we can emulate perceptrons and perceptrons have universal computation ability, then we should theoretically be able to do the same with sigmoid neurons. So that's why in this table, I have labeled the fact that, these sigmoid neurons have the property of being universally computable. And it turns out they're trainable. So like I said, if you can have any input between 0 and 1, then small changes to the weights and biases can make small changes to an input and output. And this is a very important idea that is required of a system in order for it to be trainable. And we will be exploring this more in the near future. But yeah, that's kind of just like an overall explanation of, the two major, I guess, basic implementations. I'm sure there's other things, other types of networks. I think there's like convolutional neural networks, blah, 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 all this stuff that we're going to learn about soon. So I'm basically like at the lowest level of current knowledge in this field, but that's completely fine. Everyone's got to start somewhere. At this point, I'm basically just ranting. So what's a summary? Artificial intelligence is this crazy thing. It's implemented with these things called neural networks. And there's a basic implementation of a neural network with perceptrons as the little nodes with binary input output. They're not trainable. Well, they're trainable to like a certain extent. They're not that great. There's a better version, which is known as a sigmoid neuron, which is trainable due to the fact that it has a much wider range of possible inputs and outputs. Infinite number, to be exact. That's funny because infinity is not exact. Anyways, I don't know what I'm saying. So yeah, that's basically what I've learned up to this point. Not a whole lot, but we're going to continue to explore, and there will be much more to be explored in the near future. So if you enjoyed, whatever, do whatever. Anyways, so what's next? What is next? Turns out what I'm learning next is, well, I'm not really sure. It's probably going to be, you know, according to the book, it's the architecture of neural networks. So I'm sure it's going to be the structure and how they interact and flow. And then also, how are they trainable? You know, like what computer algorithms allow for a system to be trainable? So blah, blah, blah. We're gonna talk about all that. It's gonna be super fun. It's gonna be awesome. It's gonna be crazy. You're gonna love it. Maybe, probably not. I don't know. We're also gonna be um that was probably the most stereotypical way I could have moved my glasses ever. Anyway, I'm just kidding. We're also gonna be exploring um capture the flag. It's really fun. It's really cool. You get to basically hack in an ethical environment to earn points. It's basically like a game where you hack, and it's a good way to learn how to hack. So that's what we're gonna be doing. We're probably gonna might be kind of weird to stream. I've never streamed before, but it would be kind of fun to try. At least, recording myself solve some of these problems, talk through them, work with people if anybody ever decides to watch these. But yeah, that's basically what this is. Just like an introductory intro to me self-studying this crazy stuff that's going to hopefully make me the most dangerous man on the internet. So I hope you enjoyed. I hope you learned something useful. I hope you didn't get bored, but it's probable that you did get bored. In which case you probably switched off the video. That's completely fine because this is a recording more for myself than for anybody else. But it's okay because it's not for myself, it's for everybody. And if I made somebody happy, then it's great. I'm basically just venting and justifying everything that I've done in the past 10 minutes, 25 minutes, but I don't have to justify. Who am I justifying to? If I make it on a watch list, this will make it on the news as the first introduction of the most dangerous man on the internet to the internet. Boom. Goodbye. Have a wonderful day. Hope you have a great day. Wonderful day. Awesome day.